It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Farming Doing Nice Coffee.
Hi guys, this video today is going to be all about just Kc expressions or Kc equations, depending upon which way you want to look at it. So we're going to be going through and looking at a couple of equilibriums and just what we actually use when we're doing up Kc expression, and then there'll be another video which will actually go about doing Kc calculations. Okay. Now Kc is the equilibrium constant. So what we're talking about is when you set up an equilibrium where your rate of your forward reaction is the same as the rate of your back reaction, okay, you have some reactants and products in there, and we have a value, okay. Now that value is determined by doing the concentration of the products over the concentration of the reactants, okay. That's how you get your Kc. So anytime you see square brackets, it means concentration. And so there's a couple of things that we don't include. I'm just going to show you quickly how we just work out or write down what the expression is for these, okay? And I'll introduce a couple of rules, okay? So the first rule that I want to introduce is this, all right? Number one, no solids. All right, so anything which is a solid like that, all right, you don't include in your Kc expression. All right. The second rule is no pure liquids. So we're not talking about if they're dissolved in water, that's fine, okay? But if it's a pure liquid like that, you don't include it, okay? The third rule, all right, is if you double the reaction. So what I mean by that is if you double the numbers in front of each of your chemicals, all right, you have 2 times the Kc value, which makes sense, right? If it's concentration of products over concentration of reactants, okay, what you do is if you're doubling these, you're just going to double the value of your equilibrium constant, okay? And the fourth rule that you need to be aware of, all right, is if you reverse the reaction, hopefully you can work out what's going to happen. So if you flip this and your reactants now become your products become your reactants, all right, your Kc value equals 1 over the original, okay? So if the original value was 3 for your Kc value, your equilibrium constant now becomes 1 over 3, just because you're flipping those around. So those are the 4 rules you need to know about writing up your Kc expressions, okay? And what I'll do now is I'll actually go through and show you some examples, all right? So I'm just going to start off reasonably simply, all right, just using some gases. Okay. So I'm going to go back and use a very common, very well-known equation. All right, so I'm going to do the Haber process because this will help you to see straight away what we do with some of the different values in our equation. So the Haber process is nitrogen gas plus 3 moles of hydrogen gas in equilibrium with 2 moles of ammonia. Okay, so we've put in some nitrogen and hydrogen, we've allowed this to establish equilibrium, okay, and now we've got a forward reaction equal to the back reaction, okay. What we're going to do is work out how we could write the expression for the Kc value, all right. So Kc, we know, is concentration of products over concentration of the reactants. So our products in this case are ammonia, all right, so it's ammonia here, which we put square brackets in to represent that it's concentration. We don't need to worry about putting the state in, okay? However, what's really important is knowing these stoichiometry values. So 1, 3, 2, that's in front of them. Because that 2 comes down here and becomes squared. So it's actually the concentration of ammonia squared. All right, that's the only product, so that's all we put up the top. For the reactant down the bottom, all right, we've got nitrogen here, we've got ammonia here, hydrogen here. So it's the concentration of nitrogen, okay? There's a 1 out the front, so we don't need to bother putting anything here. And that's actually times by the concentration of the hydrogen, because all of our reactants go on the bottom. So there's our hydrogen, okay? Now, there's a 3 out the front of the hydrogen, so that 3 comes down here and it becomes cubed, okay? So this 3 here comes over here to the cube section. And so that's our Kc expression for the Haber process, where nitrogen and hydrogen combine to form ammonia. It's our concentration of our products, which is ammonia, with a 2 out the front. Okay, so that becomes squared, over the concentration of our nitrogen times our hydrogen. All right, the hydrogen's got a 3 out the front, so it becomes cubed. Okay, cool. So I'm going to show you another one now, bringing in some of those first and second rules. Okay, so the next one I'm going to look is just an ionization reaction. So that's commonly where you have something like sodium chloride. Okay, so we're taking some solid sodium chloride. We're going to dissolve that in water, so it goes plus AQ. Okay, and we establish an equilibrium with sodium ions in solution and chlorine ions in solution. Okay, so it's just a straight dissolving of a solid into two ions. Now, if we're going to work out our Kc value, okay, what we need to look at is firstly our products. So we've got aqueous sodium, we've got aqueous chlorine there, which is fine. Okay, we've got no issues with having those in there because they're not solids or liquids. So it's the concentration of sodium ions times by the concentration of chlorine ions, like that. Okay, there's a 1 out the front of both of those, so we don't need to worry about putting any other numbers up the top here or anything. Okay, now it's where we get to our products that we have a bit of a look. Okay, here we've got solid sodium chloride, and we know from our rules that we don't include solids. Okay, so that's not going to get included. We've got plus AQ, or basically pure water, which is a liquid, so we're not including that either. So in this case here, there's actually nothing that goes on the bottom. So our equilibrium constant value is going to simply be determined by the concentration of sodium times by the concentration of our chlorine ions. Okay, so how well it dissolves, or what concentration we have of these, determines the equilibrium constant value. All right, let's do another one using that rule again. Okay, but this time we'll do it a little bit differently. Okay, so let's do this equation. So we're going to look at this one between, let's do a combustion reaction. Combustion reactions are really good. So let's do, even though combustion reactions aren't equilibrium, it's just good because it brings in a couple of different states. Okay, so I'm going to bring in propane, C3H8, and is a liquid. That's going to react with oxygen gas. Okay, and let's say, even though it won't ever happen, but let's say we get an equilibrium with the carbon dioxide gas and the water, okay, which is in this case as a liquid. Okay, so let's have a look at balancing up this equation. All right, we need a 3 in front of the CO2. Okay, we need a 4 in front of the water, and here we've got 6, 10 hydrogens, so we need a 5 in front of the oxygen there. Okay, so our Kc value, okay, is going to be this. All right, you look at your products. Well, here we've got carbon dioxide gas, which we can use, and there's a 3 out the front of the equation, so it becomes to the power of 3. Okay, the water is a pure liquid, so we're not going to be including that. Okay, we're going to have that over here. Propane is a liquid, so we're not going to be including that. But we do have oxygen here, so it's going to be concentration of oxygen. Okay, and there's a 5 out the front, so it's going to be oxygen to the power of 5. So that's our equilibrium expression there for this reaction. Like I said, I know, please don't leave any hater comments, but I know that combustion reactions aren't equilibrium, but I just wanted to bring in something that had some liquid on both sides, or one of the things that we don't include. Right, I'm going to show you one more. Okay, the final one I'm going to show you is a precipitation reaction. So if we've got a solution of silver ions, okay, there's aqueous silver ions, and we've got some chlorine ions in there as well, and we establish an equilibrium with solid sodium, silver chloride, I should say. Okay, so what we're going to do is we're going to look at the Kc here. Okay, Kc equals, all right, now over on this side, you notice, okay, we've only got a solid as the product. Okay, we don't include solids in our Kc value. So what do we put on top? Okay, well, hopefully you'll work out that if there's nothing here to include, the only thing that can go on top is a 1. So if your products are all solids or all liquids, okay, you can only have a 1 on the top. Okay, there's nothing else you can put there. Then we put our reactants over here. So we've got silver, which is Ag+, okay? There's a 1 out the front of that, so there's nothing else, times by concentration of the chlorine ions there. There we go, and there's our Kc expression for this reaction, which is precipitation, okay? So all we've got is 1 over concentration of silver times concentration of chlorine. All right, so there's a couple of examples. What I want to talk about is what the Kc value actually tells us, okay? Because in the next video, I'll do some calculations for you and show you how you do that, but you need to have an understanding of what Kc actually means, okay? So if you have a equilibrium constant value, which is greater than 1, okay? What that means is that you have more products, okay? You've got more products because your equilibrium constant is products over reactants. So if this number on top is big and this number is small, you'll get a number greater than 1, which means you've got more products. So that means in a Kc value of more than 1, okay, it favours the products or the forward reaction. So it favours the products or the forward reaction. That's something you can talk about, okay? If you've got a Kc value equal to 1, okay, that means you've got equal concentrations of your products and reactants basically, all right, or an even ratio of them, I should say, okay? So that means that it favours neither side, okay? So you've got an equal ratio of reactants and products, your Kc value is equal to 1. If you have a Kc value, all right, which is less than 1, okay, that means you've got more reactants. So it means you've got a big number on the bottom, small number on top, okay? And so this one favours the back reaction or the reactants, okay? This reaction here, all right, is said to be incomplete, okay? Whereas if you've got a Kc value which is big, all right, this is said to be a complete reaction. Okay, and that becomes really useful when you start talking about yields in industry and everything like that. Okay, but that's what your Kc value tells us. So keep that in mind before you go on and start doing the next video, which is around Kc calculations. All right, as always, hope this has been helpful. If you've got any questions, just ask. Thanks, guys.